What else? Okay. Now, I believe that everybody except one is in the other class, right? So who is not in the other class? Abraham and Dwayne? You are not. The advanced program. Okay. So two of you. Tamara should be there. Okay. Good. All right. I almost remembers your names. I almost remember your names completely, almost. So Anand, Dwayne, Hamika, Ami, Malintika, Anand, right? Dewey, Dwayne, and Abraham, Hani, Miguel. All right. We're missing one just. All right. So previously I gave a long kind of walkthrough of the process and talk about the differences between the three sets. I was trying to record it. You know, I was doing a drawing. I was trying to record it, but I forgot to record the screen, so it was gone. The tape was there, but everything I said was there, but it wasn't the screen wasn't recorded. So I made a video and posted on Blackboard. It's called Lecture 3 Extra Content. So if you want to replay that, it's available. And that was following the train test plate that we talked about, right? The overfitting concept. And then, you know, it was great that I was able to do another video and I mean remake what I had to say in the video, because I was able to make some concepts more clear. But anyway, so today, and just a reminder, homework 2 will be due by the weekend, right? So that's going to be our focus. Now I trust that you've watched the videos, you've read the books, or you will be reading the books. So I will not talk about concepts isolated, like, you know, dry and abstract concepts, or I'll tie the concepts when I demonstrate the process. So everything is coding focused, but the concepts are tied here. The concepts are explained in the process. All right, we'll be visiting two data sets. One is the default data set that's demonstrated in the videos, I believe. All the videos use default, and this is default number 1, version number 1. This, I believe the videos have talked about so far, talked about correlations, simple process of converting binary variables into flag variables, converting categorical variables into multiple flag variables, and simple process of z-score standardization, right? I think those are in the data science basics. Hey, now the class is complete. Cool. All right. Isn't it cold outside?
It is.
It's going to.
Onboard and Jackson and so.
All right. Right. So, and now the Adeline model process, and then the logistic regression. We'll talk about Adeline and logistic regression today. So let's set the stage. Previously, I was mostly talking about the high level, mostly highlighting. And since you have been reading the materials, I don't have to repeat these. We will zoom into these steps in the code level. Okay, so two data sets let's see. We'll briefly look at the structure of the data sets. So the first one is default. I hope you'll be able to see that. Maybe I can zoom in, maybe not. No. Well, anyway, assuming that you can see. So, or maybe I can do this. No, not zoom. That's interesting. Let me see. All right, that's better. So this default data set, that's the business context. It's the credit card company's credit card business. You know, there's monthly statements, and there might be interest incurred on any debts over time if it's not paid for. If the statement is not paid for in full, and there are 1,000 rows and 20 something columns. There's an ID column. The name is ID, so it's clear it's an ID column. It's string type. It's letters. It's unique to each customer. There's a target variable. The name is target. The data type. The data type is numbers. It's actually zeros and ones. So it's ready as a binary variable. One refers to credit default, account default. Zero means healthy or not default. So value 1 is the primary value of the target, and approximately 20%, I think, has a value of default. And there are a bunch of numeric variables. And so just because the data type of the variable is number, it doesn't mean it must be numeric variable or it must be interval variable. You have to look at the meaning, such as payment status. Value of -2 means no new charge, so customer didn't use the card. -1 means paid in full. Whatever the charge is, whatever the statement amount is, it's paid in full. 0, paid minimum due. So there's no penalty, but there will be interest on the remaining balance going forward, and such. So the values are in an escalating severity kind of manner, but this variable is not interval because the gaps between the values are not equal. So these are different, we call discrete levels of the payment status. We assign different values, arbitrary values for different meanings, right? And I can scramble these. I don't have to order the values in this way. I can randomly assign A, B, C, D, E, which becomes strings, and you cannot sort them. So even if the data type is number, it doesn't mean this is an interval variable. This is better treated as categorical variable, right? Or at least it's called interval. It's not called interval. It's called ordinal, where the levels can be ranked by natural order, sometimes numbers, sometimes letters, and the levels are increasing or decreasing in the degree or in the level, but the gaps are not equal. So that's what we call ordinal. In data science, there's no special tool or there's no special techniques to deal with ordinal variables. So depending on the, I guess, the sensitivity of the variable, whether or not it's super important or maybe only a what we call control variable, then you can either treat it as if it's a numeric or interval variable, ignoring the gaps, but only retain the key information there and see if the model pick up. And then if the model believes that the variable is very important, you might want to zoom in and apply a different strategy. But treating this type of variable as interval is kind of using a coarse strategy to reduce some of the costs of special time invested in dealing with this kind of special variable. All the others, amount of payment and payment status, that's the same. They use the same coding scheme. So all of these require a little bit of attention in terms of what strategy you use to model them. Statement amount is simply numbers, natural numbers. Year of birth, we talked about that it's better to convert it to age. And male or gender variable is a binary string type, so it must be converted into a flag variable. Education is another ordinal kind of variable where the levels are ranked, but the gaps are different. Another way to record education is years of education. So how many years of education have you received? That's going to be more interval by nature. But this one is using the years of education and then assign it to different levels. So one of the levels is unknown and is assigned level 5, which makes it not appropriate to use interval strategy to model this variable. So either, well, I don't know. I mean, this level makes it kind of difficult to model it perfectly. You can have a temporary strategy and treat it as interval, but later come back and apply more care in terms of how to deal with that unknown level. Marital status, again, it's a string type. It's categorical, not only binary, and you cannot rank them. So you must treat it as categorical variable. So that's the structure. The key variables here are that requires attention when you prepare the data sets. It's ID. You would need to remove the ID in the real data preprocessing stage. The target variable, you must extract it and assign it to Y, right? Y variable, and then recognize which of these are better treated as interval variables, which later you will apply the standardization, and which of these are better treated as categorical variable, and later you'll use one-hot encoding. So those are kind of standard process. Yeah. No, what I was saying is for categorical variable, regardless of it's in string type or let's say education, for now, let's treat it as categorical. It's in number format. Categorical variables has these different levels that you cannot simply subtract and add, because that's going to that doesn't make sense. You cannot subtract male from female, you know, it won't make sense. But for Python, the only thing that the CPU can do is the numeric operations. So what are you going to do? This is the topic of how to deal with categorical variable, and you will find slides. Which slide? Let's see. Data science basics. Previous 2 weeks before. The first module. Let's see. First module, data science warm-up, you'll find a few slides that talk about the nature of categorical variable, and then how do you deal with it in statistical models, basically. So the key here is that, let's say for gender, it's a special case. It's categorical, but it only has two levels, so it's binary. But it's string type, so you must prepare it. How do you prepare it? You convert it into a flag variable where it's assigned some certain meaning. Let's say the meaning of that flag variable is female. So when the customer is a female, the value of that flag variable is 1, indicating this customer is female. Whereas if the customer is male, the value of that flag variable is 0, meaning this customer is not female, right? So essentially, you are turning a, kind of a string type variable, a binary variable, into a flag variable where the program can now incorporate into the program. So in the same logic, if you have 3 levels, then you would have to have 2 flags to jointly model the level of that of this variable. Let's say if I have a flag variable married and a flag variable single, then if a customer is married, then the value under the married flag variable is 1, 0 on the other. If the customer is single, then 1 on the single and 0 on the married. If the customer is others, then it's both 0 for married and single. That way you can uniquely and completely capture the information. But for these cases, the model would have to have 2 coefficients to be able to model the influence of this categorical variable on the target. So that's a compromise, but that's the best way to incorporate categorical variables. Make sense? So I suggest that you also revisit the slides and the slides talk about locations or geographic locations, north, south, west, and east. And if a categorical variable has 4 regions, then you need 3 flag variables to model the complete information, right? And then that 3 categorical variables become 3 input variables in your preprocessed data set. Hopefully that makes sense. All right, and you'll see these patterns over and over. Okay. So that's default, and then churn is the focus of the homework, right? Now, although the structure is fairly similar, the number of rows are fairly similar, number of columns slightly smaller, but there are some nuances here. Let's take a look. So this data set is about whether or not a customer of a cell phone plan, let's say, maybe a landline account whether or not the customer left the company at renewal time. Close to 20% left the company and 80% remained. There's a phone number recorded, which is the string type, which is number and dash, number and dash format, 7 digits. This is the text file that introduces the data set, and you can download on Blackboard, right? You know that, right? The phone number is unique for each customer. So the best way to understand this variable would be, for analytics purposes, would be to treat it as an ID column. So this ID column does not have an ID number, or it does not have an ID name on it, but the meaning of the variable is phone, and then for if there's a role of the variable, then the role of this variable would be an ID identifier, right? And I guess that's the only thing you need to know. And in pre-processing the data set, we will drop this variable entirely. The churn is a binary string variable, records yes or no, that refers to the outcome of the churn. If it's yes, then the customer churned. There are close to 20% customers that had yes, and 80% has no. So, and this one is the target variable, right? The name of the variable is not target, but the purpose of the variable is the target variable. So you will need to know the name of the variable in order to complete the homework properly, or in order to adapt the codes from the demo to your homework in order to complete your homework. And because it's string type, Python will not be able to deal with it. So we will have to prepare it. The way to prepare a binary variable that is not a number would be to convert it into a flag variable. That you already know how to do that, right? There are 2 ways to convert categorical into flag variables. The more formal way would be the one-hot encoding, which is going to be the same for all. The other way is the simple way, or convenient way, which only would be convenient if you're converting a binary variable into a dummy or flag variable. And I'll talk about that when I demonstrate the codes. So keep in mind the names of these 2 variables. Otherwise, these names, you don't have to, other than area code, because I singled out area codes and talk about, the problems with that. But other than these variables, the other variables, you don't have to know the variable names by heart. But there are different strategies to select them in groups, such as only select numeric variables, or only select string variables, and such and such. The other 2 things to mention is there are 2 more string type variables, and both of these are dummy or binary variables as well. So we will apply the same strategy, but because these are not target variable, these are input variables, we will include them as part of the transformer process, the automatic data pre-processing process. Whereas for the target variable, churn, converting to flag variable would be more manual because it's not one of the input variable, right? All right, so just a simple walkthrough. And then here is my preparation. So I'm going to go through these processes. So my setup here is I have my homework put on one side, And then I have my demo codes on the other side. Let's see. Let me make it bigger. Okay, so get this out. Okay, so why don't you, if you want to open up your files, go ahead and do that. And at any point, if you want me to slow down, just call me and you know, shout, slow down, please. Okay, so homework on the right side, demonstration on the left side. All right, so let me also have solutions here, make sure. Okay, I will skip the conceptual questions as you know, as you all have time to study, and it's not technical. All right, so let's run these. Quickly walk through NumPy and Pandas. We had a very happy session yesterday. You know, running all of these tools. NumPy.random, we also did it yesterday. Here, we're just importing as random because we use them more often here. After importing, you can simply refer to random. And for scikit-learn pre-processing, we use standard scalar is z-score scalar. Min-max scalar is what we call range normalizer, range normalization. One-hot encoder is converting categorical variables into flag variables. As scikit-learn compose, make column transformer. Column transformer is a conglomerate or combination of different transformers. So what is a transformer? Standard scalar is, min-max scalar is, one-hot encoder is. All of these are different kinds of transformers. And I talked about we use transformers we fit these transformers on the training set. And then after being fitted, which means train it on the train set, and then we use those trained versions of the transformers to prepare or to pre-process the test set as well as the score set, right? So the process is different. So what this does is it put them in a pipeline and then tell it which columns to use what. So it's kind of a mapping process. And then by using this transformer, it's like the father of transformers, you know, or grandfather of transformers. You tell it, you know, which son does what, or which child does what on what columns, and then it will tell them to do all of these and put them all together. So you don't have to do them piecemeal, right? It makes the process very easy, very happy. So, and then moving on, we have in evaluating the models. Okay, we have the train test split mechanism here. And then in evaluating the models, we need to calculate the accuracy. Accuracy here is a decimal. It's a percentage, you can say. It is the percent of correct hits or correct predictions out of all the predictions. We're talking about binary classification here. So the percentage or the proportion of correct predicted class labels out of all the predictions. So that is the accuracy score. And the opposite of accuracy, which is 1 minus accuracy, will become the misclassification error rates. That's the error rates we'll also talk about. There will be two errors concepts, and be sure that you'll be able to differentiate both and don't be confused for one another. But I'll point those out when we are there. And then for hypothesis testing, we have the z-test and the t-test for individual samples. And then we have graphing tools, and then some styling tools. All right. And then here, we fix a certain random seed to be able to replicate the results. And be sure not to change these. All right, make sure that you have this data set in your directory. And now we start processing the data set. So recall that the churn variable is yes and no, right? It's a string variable, it's a binary, and it's a target. So the way we deal with it is we need to convert it into binary and then make it numbers. Either integers or floating points, that's fine, but as long as it's 0 or 1. And then we want 1 to indicate churn because it's the primary target value. So the way we convert, or the convenient way that we convert a binary string variable into a flag variable is we use this comparison operation here in Python, where we extract or we index the column. We talked about indexing, right? So you can for this is data frame. So the best way to index the columns or rows in or the different elements in data frame is to use ilog or log. But at the same time, if you're only getting the columns, right? Remember, columns are special in data frame. In data science, columns are variables. So the purpose here is to only get the churn column. So I can use bare brackets and to indicate, and only one level of bare brackets, then I'm getting a series. I'm downsizing the two-dimensional object into one-dimensional, becomes a series. And then I use the name of the column to slice the column. So bare square brackets, quotation churn. This will get the churn column. So I use the churn column to do comparison with yes string. What it does is it will do pairwise comparison on each of the elements and return a same shaped series with yes or no. It's a value with true or false, sorry. It will return a Boolean, which is logical, a logical column indicating yes or no, indicating true or false. True meaning the value of churn is yes. False meaning the value of churn is no. So after this operation inside the parentheses, what I get is a true or false logical column. And since I need numbers, I need 0 or 1, then I convert it to float, and then I assign it back to the original column. So after running this cell, the original values of the column in the data frame will be changed. So be cautious about that. Okay, do that. And this operation was not necessary in the demo material because the default, the target variable default, or the target variable is the name is target, the meaning is default. It was already in number format, so you don't have to do the same, right? So this part is special, slightly special, but since it's not part of the problem, you simply run it is fine. And some special notes about area code. It's numbers, but it's not numeric. Oh, I mean it's numeric, but it's not interval variables. The area codes, like your area codes. What's your area codes? Hey, let's do a game. What's your area codes? 713? Almost, I guess. And anyway, what's your 862? 862. It's also Houston. It's not Houston. No, 833 is Houston. 713. What else?
708.
Huh?
084.
08. 08.
77.
No, that's zip code. I mean, area code. Yeah, area code is the first 3 digits of your phone number. 346. Zip code is the 5 digit. So, yeah, when you call a phone, then the first 3 digits in parentheses, that's the area code. What's yours? Other than Houston,
It would be 812.
812,
281.
281. It's Houston. No, or it's close. Maybe it's close. Texas. Right, I've seen 833,
813.
813, and 713. Yeah. Oh. Close. Well, I guess mine. My number is from California. Which is close to LA. The town is actually Big Bend, you know, the Big Bend. Pasadena. It's 626. My area code. So that's how I can quickly tell if somebody's calling me, is that a scam? So if it's not 713, it's a scam because, you know, they don't know I'm living here. They thought I'm Pasadena. So all numbers are from close by areas, or at least what number looks like. Okay, so that's the area code. So area code, if it's a column or if it's a variable, you wouldn't believe that it carries intelligent information to tell you what the customer is going to do, right? It's just assigned for some, you know, location-based reasons. And most of the customers will share the same the same area code if they live close by. So that variable is not going to be very interesting in a way. But anyway, regardless, that variable, if you want to include it in the model, then you cannot treat it as an interval variable, right? You have 713 and 813. Say your number is 713. My number is 813. Am I better than you? In any way? No, it's random. So area codes are better treated as categorical, right? That's why we do a special operation here to convert it to categorical. The code name is category so that we don't get confused. And just run it through, and then you can look at the list of variables here and their data types. That confirms the document that I just showed you. Okay, so now the first question asks you to extract only numeric variables, but be sure to drop the target variable. And of course, you shouldn't select the ID variable, right? It's always a good practice to look at this table of variable types and variable names and types and make sure that you will get what you intend to get with your codes. So if I were to select numeric variables by using Python codes, by using the function select columns, then I will get churn, account length, not the area code because it's converted to category, and everything here other than international plan, other than female plan. All right, I don't have to worry about phone because that column is objects, which means string variables. So it's not going to be selected anyway, but churn will be selected if I don't drop it intentionally. So what I need to do is I will look up the codes here in the demo. So what you can do is copy paste. For beginners, I strongly recommend that you copy paste and then adapt the codes rather than typing manually. All right. So now, is it ready? Should I just run it? No, there are a few things you have to do, right? This is what we call customizing the codes or adapting the codes. Now, first of all, there's no column whose name is target. But the purpose is to remove the target variable if the target variable is a number type, which turns out to be true. So I have to use churn, right? And what else? There's no DF default. The data set name is different. Here it's churn. Now I like to use tab completion because it reminds me the exact names. Make sure I don't have typos. And anything else? Is it ready? Also read the requirements. Read the requirements, right? Requirement says must assign it to X numeric no DF. All right, so this completes the first step. And then afterwards, well, you can run it to confirm it's running. Okay, all right, that's good. So then the next step is to apply Z standardization on all of these selected variables, assign it to X numeric Z, and then convert it to data frames using the same columns from the original columns. Now, the first thing I'm gonna do is to copy and paste, and then carefully read the codes. Make sure that standard scalar is imported. You are at your discretion to choose the name here, but we can use the same name. Z scalar is an object. This line defines a brand new instance of the object, and then we're going to train it based on the X variable from the training set. And then, so what it does is the scalar, remember what scalar does? Z scalar will calculate the mean and standard deviation of the variable or of each of the variables and remember them one by one. And then the transform part will then subtract the values of the variables by the mean according to the variable. It's variable wise differently. And then divide the value by standard deviation of that particular variable. So it does everything in once for all the different variables. And how does it make sure different variables apply different values? Because different variables have different means. You know, the way is to leverage the matrix format, and it will do I guess think of it as broadcasting. You broadcast the same parameters, mean and standard deviation of the same variable across the rows. So you apply the same statistics on the same variable, and then when you switch to a different variable, it applies a different sets of parameters. But everything is, you know, in the back end. Everything is programmed, everything is robust. The function, I mean, the object will do it well. So there's no need to worry. But anyway, just know that there are two processes going on here. There's a training process, fitting, and then a transformation process, which is processing. After that, we get a NumPy array without the metadata, and then we turn it into, we have to define it as a data frame using the columns that comes from the original column. All right, first of all, let's fix the codes. Anything I need to change? Well, the DF will have to be stripped because we dropped that. And here, what else? X numeric looks fine. The requirement says we have to assign the scaled results to X numeric Z instead of scaled. So let's change it to X numeric Z. Just to make sure, copy paste, and then you'll have to do the same, replace it here. And then replace it back as well. Okay, just to show you a trick, let me go back that I have scaled. Now, there's a find a replace function here. When you highlight the code, when you highlight the cell in command mode, you hit F. Then you are able to find everything. I mean, you are able to find anything that you want within the cell. You're able to see all the instances and then confirming these. Sometimes when you're searching very short terms, some other terms get selected because that's part of that term. Be sure, you're not mistakenly replacing. Here is fine. Scale, there are 2 times. I like to replace it with X numeric Z.
Find and replace.
Sure. Make sure it's blue, not green. Green is when you can edit. Blue is the command mode. You click F. Then, F, find. No control, just F. And then you type in the replacement term and you can either click enter or hit enter or click replace all. And then everything is replaced. Very neat. And here, make sure it's X numeric Z. And using Z to define data frame, using the column from X numeric. Now, this is not always applicable. You cannot always use this trick, by using the columns of the original data set, because sometimes in pre-processing the columns change. Especially when you have a column transformer, and then that includes a 1-hot encoder. And that way you will have more columns than you started, right? Because the categories in a categorical variable will be unpacked into additional flag variables. So you'll have more variables than before. Then you cannot use the original variable names to assign it to the pre-processed data set. But here you can do that because the only thing that we're doing here is Z standardization. It's not going to change the columns, and it's not going to change the orders of the columns. So we can do that. After that, let's run. I think it's ready. Let's run that, and then you can run this sanity check to look at the statistics after pre-processing the variables. The means are all very close to 0. The standard deviations are now 1, so these have been standardized. The values are mostly in between -4 and +4. All right, very good. Questions? Now, after that, you're ready to start to construct the for loop process for add a line. Before that, you will need to have the X and Y variables to make it easier. So the X variables are the standardized variables that we had just now, just reassign, whereas the Y variable is the churn after we have replaced the values, right? We have replaced values of churn in here. In here. Now the churn, not here, sorry, in here. The churn variables are now in floating points, having values of 0 and 1. So we can do this. And then, of course, you can, confirm a few things. If you are curious, the X is going to be the same because we did a simple copy. X is like that, but the Y variable is going to be, let's see. So value counts will tell you what are the unique values here, and then how many of them are in this variable. So I'm looking at value 0 and 1 as the only two unique values, and then there are 419 of them with value 0. So, just the high level statistics. All right, I'm going to remove that. Initialization will draw random numbers for the coefficients, and then you will define other critical values. So remember this. You get the dimensions of the X data set, and here N and M is, I believe we're not going to use them per se, but the reason I extract that is because in the process layout, like these, when I have notes, my notations on the formula and the matrix form, I also have the dimensions of the data objects. All of these you can download from Blackboard, but I have these to quickly show you. Single layer, this is add a line with notes. So these are the green color would show the dimension of the data objects throughout the process. So this is, all of these are math. They are super boring, and I don't want to look at more times than I have to, but these data objects and dimensions, these are pleasant to look at, and these are one way that you can trace the process, with pleasure. And it's a good exercise to always stay on top in terms of what is the object I'm getting, what is the dimension of that, and what does that mean, to fully understand the process. So that's a good mental process to keep track of the shapes of the data. And here, the X as training set, the input data here, the number of rows is N. We will stick to that notation throughout the neural networks model. N is the number of rows, which is the number of samples, or the sample size, or the number of training examples. M is the width, is the dimensions, is the number of variables in a pre-processed input data set, right? It's not necessarily the same as the number of columns in the original data set because you haven't pre-processed yet. After pre-processing, you sometimes have more variables. So M is as many regression coefficients that you need for logistic regression, other than another bias term, which we'll talk about. So, I'm getting these just to demonstrate. We'll use epochs here, and keep in mind, epochs here, sometimes it has misspelling. Here it's a misspelling, but I'm going to stick with it. It should be epoch, E-P-O-C-H-S, without the E in here. But as long as you keep it consistent, as long as you stick to the same in the same session, it's fine. Later, I believe beginning with neural networks, or beginning with the exam, inside the exam, it may be missing the E. So from that point on, it's all another way of spelling, but within the session, it's the same. Remember ADA? Eta is a learning rate. And if you went through the demonstration, you realize that the models are quite sensitive to the choice of eta. For eta line, you would need a smaller, much smaller eta in order to make it work. Otherwise, the cost function will explode. So that's a very good exercise to observe and think about. But we don't have time here. You can look at the video, the homework assistance video. It talks about that. All right, and then we generate random numbers for the weight vector. It's a vector. We use origin.normal. I think Hani asked a question, can we use normal yesterday, right? Did you? Or maybe not you. Oh, Anand, maybe. Anyway, somebody asked the question, and here we're not using the rand n. We're using origin random number generator, which has a tighter control on the pseudo number algorithm. So we can replicate the same results more easily. But this normal is going to generate normal distribution with location and scale parameter. We're drawing numbers with a very tight region with standard deviation 0.01. And then we are drawing a vector of size m+1. Why m+1, not m?
Bias.
The bias term, which is at the beginning. We always put it at the beginning because sometimes we call it W0, right? So weight 0 is the bias term. So the number of parameters that are going to be learned from the algorithm is m+1. And then we also create a placeholder, which we create all zeros for now, as the delta W, and delta W is what we going to calculate based on gradient descent, and then put the values into this placeholder. All right. With that, we're ready to start. Now, for eta line, let's find the process here. Similar initialization step. And then there are 5 steps, basically. The first step you want to do is to calculate net input. It's part of what we call decision process. Let's look at the slides. So after initialization, we have the decision process. The reason it's called decision process is because we have the inputs. We have the inputs and then we have the coefficients. Right now, the coefficients are randomly generated. So it's a starting point. It's not a good model. It's a poor model, actually. But over time, it's going to learn. We multiply the input with the coefficients and then add all the terms together. Then we have a sum of the information in linear terms. So it's net input, it's a raw inputs after applying the weights. It's like when you're making decisions on you're buying a pair of shoes or you're buying a laptop. You're going to gather information about price, weight, specifications, and other things, warranty information, everything. All these are input variables, and then you have your own decision rule. You value screen size, you value CPU, but you don't value too much about other things. I guess, comfort of the keyboard or something like that. So you will discount some features while you'll also emphasize the other features. These are your own ways, your own versions of the coefficients. although everybody shares the same raw input data, which is, the features of the laptop. The reason that you favor this laptop over the other is because that provides the features that you prefer, right? So this is very similar to a decision process. And then when you have a model that's trained and optimized, then when you make predictions for new cases, and you're going to process the forward loop one time with the updated weights. So you'll also, in that process, the first process of the forward propagation is the net input. You put the input and the weights together, calculate the weight, and then you calculate the activation. So activation will be the next step. All right, so let's complete this. I would copy and paste the Z. Now, check a few things here. Is X correct? Do we have the X? I think we do. X is the processed numeric variables. Do we have the WOs? Must be. We use the same format. And here, remember the dimension of X? N by M. There are M columns. To multiply that with a vector, you need the vector to have M elements as well. M rows, but only one column. Right? So, and remember that the weights vector has M plus one element. So you cannot simply apply the entire weights vector, but you have to select the M elements. And those coefficients that correspond to the variables begins with the position 1. With the position 0 is dedicated to the bias term, right? So these coefficients correspond to each of the variable in the X data set. And then after doing the multiplication, you will add the additional bias to the net weight, to the net input function. And that would be it. Verify that you get the same numbers. Let's see. That's right. Okay. And then the next step is activation. Once you have the net input Z, for add a line, the activation is linear. Basically, it does nothing. So what's going to happen is we multiply that by 1. Why don't we just skip it? Well, you could, for the purpose add a line, you can simply skip it. It does no harm. But the reason we incorporate here is that when you compare logistic regression with add a line, you will notice that this is the only place that you're going to change. All the other codes wouldn't have to change at all. So that's why we retain it here so that it's easier to see the differences. All right, check the codes. Z becomes ZX, it's fine. So, but this is only half of the steps. After calculating activated value, you would need to calculate the error term. So error is the difference between the Y target values and the activated value. The order is important. Y value always go first because this error term is going to provide a signal both in terms of the size of difference, but also the sign, the direction of the difference. It's going to feed back into the backprop, the gradient process. So it will be dangerous if you switch this around. You'll get the result completely Doesn't have to be opposite direction, but it's completely off. So make sure you understand this logic. And then, I mentioned that and compare the values, make sure you get the right. I mentioned that there are two errors here. There are two errors that you need to differentiate. There's an error inside the loop that directly relates to the raw data set. We call it adaptive error in the context of the data line. But later, when we talk about logistic regression or neural networks, the concept doesn't change. The logic doesn't change. So we'll keep referring to adaptive error, but it's long to type, so we typically just say error. All right. There's another error concept outside the loop. Hopefully you can read. Outside error, we typically refer to prediction error. So this is the dimension. This is at the model level or model level, not the data level. This is a model level. So after the model is trained, we look at the predictions, or let's say in this case, it's classifications, binary classifications. We compare the classified labels for the target, and then we compare the ground truth, the actual Y labels, and then calculate how many wrongs and how many corrects, right? So we take the wrong, the misclassification cases divided by the total cases, we get the prediction error. This is at the model level. So it's only a number, point. That would be a horrible model. 0.05 prediction error. So, sometimes bigger 0.15, but it's a decimal. But here, the error, the adaptive error would have similar structure with X. X has n by n column. And because error is y minus dx, like that, and y has n rows and one column, we act the same. So the error, adaptive error data set or data objects also have one column and 10 rows. Each of the term corresponds to the amount of errors that the current model is making, or the distance between the current model and the ideal level. The distance that the model needs to learn before it becomes more perfect. So two different errors, they might have the same name, in the questions, but you want to be able to differentiate which one are we talking. Okay. Oh. So let's finish off at a line before we take a break. Once we have the error, then you're going to take that information and be able to calculate the gradients. So all right, gradient. Gradient is part of the back propagation stage. Gradient has a simple, elegant formula where you can adapt and make sure you don't miss the negative sign here outside the multiplication. And then think about the dimensions here. X has n by m. X has n by m. And error has, we just talked about it, error has n by 1. So you cannot multiply them without transposing. So you have to turn x the other way, and x transpose becomes m by n. And then you can multiply with the error term n by 1. And then in the end, you get n m by 1 vector for gradient. So what is gradient? Well, let's try to make this work. So what is gradient? We cannot demonstrate in high dimensional cases, but we can make it simpler. Let's say, so what is a gradient? Think of a gradient. Every coefficient has a gradient. So think about, let's take one variable, let's say H, or let's laptop, CPU. So how does CPU influence your decision? The bigger, the better, I guess. But for the model to figure out how much influence CPU has on your decision to buy a laptop, it starts out with a randomly picking a coefficient, let's say -1. Yeah, obviously, that's not right. So CPU should increase the appeal of the laptop. So it should be positive at least, right? And but it's not too much. So the model can be guessing too low or too high. To make it simple to graph, so just realize that this thing that always happens, it's not because of the stylus, but because of Microsoft. That this thing always happens, very, very annoying. I'm using my my mouse, and it still happens. I guess I cannot write too much too quickly. So, that's not good. All right. Okay, so the cost, so the reason we call it gradient descent is we try to pick the optimal value of the weight coefficient in order to minimize the cost. What is cost? Cost is the total amount of errors across the data set. So here we calculated error. Error on every cases. Some of the cases, the model gets right. The error is minimal. Some other cases, the model is making more mistakes. Across all the cases, you aggregate the error, it becomes a cost. But you cannot simply add them together. You have to take the square because errors has negative and positive. You add them all together, it cancels down, right? That's not right. Error is whether or not you guess too much or guess too little, it's error. So you take the square and calculate the sum. That's called sum of square. Sum of square is the error of the model. And then in the multi-dimensional case, it's a plane. You know, it's a high dimensional plane. But let's say we only have one variable, CPU. If we take a square, and then this is CPU, and this is error of the model, or we call cost. So it goes like that. CPU, no, this is the, sorry, this is not the value of CPU. This is the weight that's assigned for this variable CPU. So what happens is, as we begin the training process, we randomly pick the variable. We randomly pick the weights. It can be high or low. So let's say if CPU optimal value that minimizes the cost should be 0.5. So this should be the optimal value, but before learning, the algorithm doesn't know. So it randomly pick one. And let's say it randomly picked this value is -4. Obviously, it's not right, but you would have to start somewhere, right? Okay, so at this place, you calculate the error. It gives you an error. The error is not optimal. So what can you do? The concept of gradient is this tangent line where the slope is the gradient, G. So this slope is very steep. It may be -10. It's -10, right? It's sloping down. It's very steep. It's -10. So this is the gradient that we are calculating. How is it important? How is it useful? Why do we need it? Once we calculate gradient, what we can do is we are trying to find this point for the computer to find this point automatically without telling it, right? The algorithm can use this information, both the sign and the sides of gradient, to try to nudge closer to the optimal point. So there is a direct relationship between what is going on, delta weight and the gradient. So if the gradient is -10, then you need to move quite a distance before you can reach the optimal region. So that's why -10, the size of 10 is large. It helps move more distances, and the slope is negative, but you want to move to the right. So you want to move in the opposite direction of the sign of the gradient. So that's two key information that you want to do, but still 10 doesn't give you the appropriate scale of the value. So you need eta to kind of soften the distances, because the scale of the weights are very small, but the scale of the gradient can be very large. So you need eta to kind of modulate the size of the move. So across all of these, so combining all these information together, once you have the gradient, let's run this and make sure that your gradient looks fine. Okay, so you can see that the second term here, although this is kind of randomly picking, but this one is already -120, 1.2 to e to the second. So it's -120. The gradient is very big, but you cannot move that much for your weights. So you need eta to modulate. And that's why, in the next step, when we calculate the delta weight, we will calculate the weights and the bias separately. But here, we take the gradient that we just calculated and multiply by eta to soften the steps. And then also we have a negative sign. That's the two things we talked about, the sides and the direction, right? So hopefully at this point you understand why gradient is important, and then how gradient leads to a more optimized weights. But for the bias term, we're not following exactly the same, which means we're not using gradient per se for the bias, because gradient is only related to the x variables when the real information is provided. But the bias term is not related to any particular information. The bias there is more of a balancing term. It's like intercepts in regression. It's a balance. It's an average of the leftovers, if you will. So there's no learning per se going on for bias. The only purpose of bias is after you have learned everything, I'm here to balance you. So that's why it is taken, after all the formula, after the deriving the formulas, what ends up being the formula for the bias, for the delta bias is the sum of the errors. And these sum of the errors sometimes cancel each other, right? And that's why it's a balance. It's an aggregate of term. So long story short, you have the delta, and then in the end, we will update the weights. And you can skip the middle points. What happens is we have obtained the delta weights. We apply the delta weights onto the old weights. It becomes the new weights. After we have the new weights, we update the old weights so that in the next round, the old weights is from the previous round, right? So don't forget to do that. Otherwise, your algorithm, your weights are not changing. This step is also critical because we keep using the old weights in the net input. All right, run this and then I get the weights. So this completes one loop for the L-line model. Now, one last point. What is gradient? How do we calculate gradient? So remember, each of the coefficient has its own gradient because each of the coefficient moves somewhat independently of each other, right? The variable CPU has its own coefficient. Laptop weight has its own coefficient. Their influence on the appeal of the laptop and your decision is independent. So gradient, what we call gradient is a vector of multiple terms, and each of them correspond to one of the weights. All right, other than the bias. The bias does not have its own gradient. So if we have m variables, then our weight vector has m plus 1 size. The first one is for bias, and the other m are for the weight coefficients, but the gradient only has m elements. Make sense? So that's why when you transpose x, what do you get? You get m rows. Each of the rows are for one of the variables. And then you collapse all the information from different sample cases with the error term. And then you get one gradient for each of the coefficients. You get m by 1 column. So that's all. Make sure that you compare the values. Let's see. Yeah, make sure you get the same values here. And let's take a short break. Let's come back at 7:40. We'll continue with the logistical question.
On this one, so it's so hard. You did something more than I didn't know today. I was being started and I didn't even know. Okay, once it gives the same answer to the right aspect. No, why? Because we're rewriting because every single time they just leave us to go from it again. Okay. Whenever I have to read it, I just hit those. Did I say? So what we did is, let's say U is 1 and O is 3. If you rerun it again and you're saying, let's do U plus O, so instead of it being plus U, we're adding 1. So if you keep rerunning, the numbers are going to keep getting bigger because it's getting bigger. So if you want to rerun your code, you have to restart something, otherwise you're going to be going. So you're not going to get the original. Yeah. That's just.
Oh, 60.
You stay out there. Yeah. Okay, that's what I got. Yes, so it's so you do it more than around. No, so good. We started. Yeah. Yeah, it's not like it's really it's so good. Click on it. It is the big, this is the only out. So no. This is this thing, right? Like. But this one runs on stuff. The one next to it, it's gonna be run. The one next to it, you should. But if you click here, simple. And then you can find it on all the roads, those do. Are you saying? This one also does the same thing, run and clear out, but that's what this one does. Yeah, it's your top ones. Faster. Can you scroll up towards
Which one?
the end of question 3,
This one,
the previous?
the homework? Sure.
You, oh my god, I'm kidding. Oh, okay, let's see. Okay, please read it, I did. It's all rerunning. Wait, is maybe these are all this.
Having trouble?
The output is different.
Although we just have to figure it out because that's precious. So if you're able to figure out what's wrong, that's gonna be yours.
This. Stay here. For right before giving a question. Yeah. My output is the same. Okay. Or that's good. I was guessing that as a person, but each time.
That happens so,
Well, this is.
that happens also when you put the board together.
Check out.
Anytime that is.
Okay.
And it's not with always, always. That's good.
Yes, exactly. And then we have the female instrumentation, which produces the same here. Right? That's all the same there. And then we have our two stem concepts. So this is the same here. You remember all of them. Why is it? We start here. Everything's the same. No, we ran it twice. No, that's because I ran it, but that's just importing the packages, so that should do it. This is great. Oh, yeah, yeah.
Still figuring it out.
It's still showing different numbers.
Okay, let's Let's up the game a little bit. Then borrow one. Up that kind of slow. Do the screen and let's run it down. As a class.
Now, no.
Make sure you don't have any secrets here.
I don't.
Well, otherwise, we're gonna find out. All right, debugging is a big part of this class. So. Okay, so at which step it still looks good and which step it starts to?
17, for the one the mouse is on, that output's the same. It's for 19, where the numbers are different. The 0.745 is same, and then all of the rest are different.
Okay, let's see. Um. 729. No, it's already showing differences. So what happens is this 0.05, if it's negative 0.05 on mine, if you look closely. So there's more deeper differences there. So so let's check. To the previous step. And here, you need to have positive. So it's over here. It's 3 negative for me, 1 positive. So good. So as I suspected, you're missing a negative. So there should be a negative here. Yeah. All right, problem solved.
Thank you.
Okay. Now, debugging, and also something that the girls already learned is that when you find something, when you find a bug, and then you correct it, and then don't just rerun from that point on. So you need to go back to the original point, not all the way up, but to initialization. Run through initialization. All right, very well. Let's keep going. So for logistic regression, the learning process almost is the same, other than the sigmoid. But the data pre-processing is going to change a little bit. So previously for aniline, the problem was simplified. We only use the numeric variables, right? So we only had to do the standardization. But now we're going to pre-process both the categorical and the numeric. And for numeric variables, we're going to use range normalization, because in neural networks, we'll use range normalization more than standardization, even though they probably don't change the results too much. But as a general rule of thumb, for neural nets, it's better to use min-max. So, and here we're going to do the split as well. So, you know, the game is kind of leveled up. So with train test split, the first thing you do when you have a data set, after you have kind of taken a look at surface level or understood the basic structure of the data set, is to separate them into X and Y first. before you do the split. So that's what we do. For the X, we're going to drop the ID column here, right? And ID column is not named ID, it's phone. And then we have to drop the target variable as well. The Y is the target term. So that's fine. All right, so for question number 4, we're going to do a split and then do the hypothesis testing. So this is going to be similar to the previous homework. I'm going to quickly go through this. And we look at and this is where the demonstration was trying to, I mean, it didn't fully unpack the process, but when the for loop was constructed at first and run for the first time, the cost function exploded. You know, you have 10 to the 18 times. So that is extremely large. It's not minimizing. It's increasing. So, and this is because the ADA learning rate is too large. Once you reduce it to have 2 more decimal points, then the learning curve is beautiful. So for models like Adeline, this is very basic learning models. It's more sensitive to the learning rate. With more advanced models, it's less sensitive. All right, with logistical regression with training test split. So we are going to do that. For here, we already did that. It's not part of the question. So in order to do split, you can almost completely copy. Let's copy the line and let's customize. So what do I have to change here? Signs? Size, test size. The question asked for 30%. Okay. The random state was defined up above. Shuffle, make sure shuffle is true. This should be fine. And in Python, there is a end of line symbol here. So if the line is too long for you, typically it's not going to be a problem because here I'm splitting the screen. That's why we can't see the line completely, and I'm increasing the size. If I zoom out, it's going to be easier, but the end of line symbol is slash. And then if you know, these 2 lines, regardless of the indentation, Python will assume they are the same line. So it will run without problem. But just to illustrate that. So I'll quickly run that and no problem. Then I'll just keep it in the same line here. But then we'll need to do hypothesis testing. Okay. So the process for doing hypothesis testing of a z-test on the proportion of y values would be similar to the example here. The only thing that we need to change is, what do we have to change? Nothing. We don't have to change anything. You know, value counts are getting the different values, the counts of different values, and then using this is using the column slice. The slice of value of the value 1 will get you the count of the values in Y train that equals to 1. That depends on the values, actually. If the value is strings, you would have to use that as label because that's the column label. Here, the column label is actually numbers. All right. So not the column, the index values are the index labels are actually integers. All right, so for the train and test, you get the count, and then you give them to the proportion test, and you calculate that. So this is here's a reminder to conduct a z-test or conduct any hypothesis testing. You want to state a few things formally to be part of the process. So for hypothesis testing, you want to state the null hypothesis. Here, the null hypothesis is the proportion of customers who churn is the same in the train and the test sets. So that's a null hypothesis. And then result and also state the alpha level. Alpha is chosen as 0.5 as a common value. And then the results tell us that the p-value is 0.13, which is smaller than alpha. This is larger than alpha, and therefore the null hypothesis is not rejected. Conclusion would be to restate the null hypothesis one more time, because the null hypothesis remains true. So the conclusion is that the proportion of customers who churn is the same in the train and test sets. So the hypothesis testing is complete. All right. Now, once you have splitted the data sets, oh, you can't see? Yeah. Maybe. Well, you have the video at least. We'll watch the video. Maybe I mean, it's blurry, I know. So, you can log on to, you can join the meeting and then for a moment look at the screen. But turn off your mic. All right, for question 5, we need to use pipeline. So, the process is similar to when using a simple pipeline, a simple transformer, but this time we're putting multiple transformers together, right? So for the categorical variables, we need to define the 1-hat encoder, specified to drop the first label, always getting k-1 flag variables, and then define it as 1-hat encoder, and also define 1-hat columns. And we said that there are 3 variables in the input variables in the input data set that are categorical, including binary. There is gender, education, and marital status. Let me come back to the churn data set. And I don't have Zoom yet, but so very quickly, wait, do I have gender? No, sorry, we don't have gender. I get completely mixed up. So these are variables from the other data set. These are variables that have to be changed. So what are the categorical variables that we have to convert? So churn is a categorical variable, but that's target. It doesn't apply here. We have area code. Area code is categorical if we want to include that variable. We also have international plan, that's binary, but also needs conversion. We have female plan. So we have the 3 variables we have to include. So area code, international plan, and vmail plan. All right. So run that. And then for the numeric variables, we will use min max scalar. And we copy these. Min max scalar, we name it as min max scalar. And the columns, be sure to modify the columns list object name to remove the scale because the question didn't ask for it. And also here, the technique that's used here as well as in the demo is that in the X data set, we have already dropped everything else. We have dropped the ID column. We also dropped the target variable. We only have numbers and categorical variables. So if we already had the categorical variable list, then what we can do is to get columns from X. We get the columns from X, but this time it's X string. That's right. We get the columns from X string. But before we get the columns, we drop the columns that are in the one hat list. So that's the opposite set, the complement set of all the variables in the training set. So this technique lets you get the longer list without having to type manually. All right, and then we can run that. Once we have the two transformer and the two column lists, we can define the column transformer. So I'm going to, and here I don't have to use the end of line symbol because it is part of that pair of parentheses. So you don't have to do that. To make a column transformer, we put them in tuples. It's like a list formation, and then each is a pair of the transformer plus the list of labels. Use the one-hot encoder transformer on the one-hot columns, and use this min-max scalar on the columns from min-max scalar, and make sure that you modify the codes here. And that would be that. After that, I'm ready to apply it to the train and test set. And here is where things differs. Recall that I said you would have to do both training and transformation on the train set, but you only do the transformation on the test set, and you only do the transformation on the score sets. And this is where the codes differ. When we use transformer, we use fit transform on the training set, but only use transform on the test set. So this is very critical. This will affect your prediction results without you even realize. So the additional step here is to convert it to data frame. I'm not reusing the column names when I convert the scaled data set into data frame because the number of columns have changed. There's no way to simply, reuse the column names. So that's why these are data frames without the meaningful column labels. It's going to be 1, 2, 3, 4, 5. But even that makes it easy to get the statistics for the data set that have been pre-processed. All right, so far so good. You got an error. It could be several scenarios. Let's see. All right, I'll pause here. Take a look. Something that I mean.
So, you know, like one, I don't think, it's in that table, so it's a. Hopefully. Well, that's it. So for one place. Are you good? And, first is also necessary, right?
Yes. Yeah. Right, okay, so just to recap, in the first homework, you did the simple de-standardization. And you also did the simple blank variable that's called manual process, right? You did each individual variables. Starting from this point, we're going to use the formula more automatic. Okay, we'll stick to that. And that's as much data pre-processing as we will do here. On the other course, we're going to do more. We're going to deal with missing values. Sometimes we'll need to do logarithm transformation. So, but every of those steps can also be incorporated into Common Transformer. The only difference would be that you have a longer list of transformers. Right, so that makes it very easy to expand the tasks. But here, we're not going to make it more complex. Are we good? Hammer, are we good?
Great.
Okay. Don't rush. Carefully look at the codes. All right, I'll say a few, and then I'll pause. So for logistic regression, the initialization looks the same, other than that when we get the dimension of the data set, we use X-train process. And now we have the process. Oh, let me mention one thing. It's better here. So after we have looked at the statistics for the pre-processed data sets, we confirm that the min and max are 0 and 1. For the test set, though, you notice that the min and max are not necessarily 0 and 1. And this is because we are not fitting the range normalizer on the test set. We're using the minimum and maximum values from the training set and to anchor the values in the test set. Right, so the test set process value does not align perfectly with 0 and 1, but that's good because we need a proper anchor. The anchor is from the training set. We cannot anchor on the test set. That would be resetting the anchors, which means, you know, misleading the models. The models are trained based on those training set anchors. We cannot change those anchors. Make sense? So when you examine the process data, the training set should look perfectly because it's the standard. When you look at the test set, as well as the score set, the stats may not be perfect, but it's completely fine. If you find perfect stats, that would be your indicators of something might be wrong, right? Okay. One last thing, after you have confirmed the stats for the process data set, you want to do here, it's not, I didn't include it for simplicity, but it will be better if you do an additional step to convert the data sets into NumPy arrays. And here it's not as critical because of the reason I'll talk about shortly. But as we move to neural networks, we're going to do more matrix multiplication, matrix processes. And over there, the metadata of data frames will make it very difficult will produce more errors. So that's why it's better to stick to the arrays. Either dot values or true numpy would be equal. But we will need to do both the X train and X test as well as a Y. Y train doesn't have pre-processed. Okay, have an error or true numpy should have an underscore. All right, so these are numpy arrays. It's not critical in this homework to do that. But if you form the habit, that would be better. Okay. Now the initialization step is almost identical. Other than that, the eta is kept large in a sense. It has only 2 decimal points. It's fine for logistic regression though, because logistic regression has a way to be less sensitive about large gradients. We keep epochs as 15. We get the dimensions from X-string processed, and then we can begin to build the process. And the process, if you refer back to the align process, it's almost completely the same. So other than the X objects and Y objects, so you can almost copy and paste the whole thing. Here, what I'm going to do is I'm going to use this complete for loop and just cut and paste different things over here. So that the net input involves X-string process, that's fine. I'll run them together. For the activation, it involves 2 steps. A clipping step and to apply the sigmoid function. Examine the values, it's fine. All right. And I think I need to calculate the error as well. Here. So error is the difference between Y train and ZF. Calculating gradient involves the multiplication and the negative sign, be sure. And then calculate the delta weight in 2 steps. And then we will update the weights. Update the weights. And then finally, something that's new here is to calculate the cost. Here, the cost function is, although the cost function are sum of squared error, and some of the students use sum of squared error here as in the align model, but for logistic regression, we have a slightly different form of cost function, which is more it is more intuitive and will give the cost value slightly less scaled. So it's easier to manage here. So we'll use this cost. Function. Make sure that the y object is the correct. And compute the cost and assign the cost. Here we don't have to, there's no cost values list here, so we don't need the last line. And then get the cost. Okay, now I'll run this in one shot. Make sure that you get 242. And that's right. Okay. So the only thing that's different was the sigmoid function, right? So let's talk a little bit about the difference. Oh, there's a good illustration of the add-a-line process. Now let's take a look. So in the net input stage, we have the inputs, the dots, the input neuron, and the weight coefficients as a vector. W0 is the bias that does not associate with any of the input variables. It just associates with a constant term. So it's not learning by the information, but it's balancing the information, balancing the errors. And once you have that, then you have the net input. It's the sum of all the terms. Then you go through the phi activation process. For add-a-line, it doesn't change anything. It's a linear transformation applied by multiplied by 1. So it's essentially the same as the net input. So the net input can be very large. The net input can be 1,000 or negative 1,000, right? So think about the possible errors. And then you calculate the error. You compare y value target with the activated value, which is the net input. So what is y? Y is 0 or 1, just that, right? So so this is y-axis, and then let's say this is the net input. Let's do this. So if this is fine, this is activated value. This is the, then it's going to be the same. And then, but in terms of y can only be 1 or 0 as the outcome. So if z is very large, the prediction, the activated values will be the prediction or the predicted probability of for the target. So if z is very large, the predicted value is going to be huge. And you take the difference. This is the error. The difference between y and psi. So this is the amount of distances that the algorithm will have to learn to correct this to bring it back close to 1. if the value is 1. Right, so once you have the error, then gradient is calculated like that we talked about, based on the current weight position and so of the optimal weight. You calculate the gradient and then use that to, of course, the gradient is calculated based on the taking the derivative of the cost function. So once you have the gradient, you calculate delta weight based on the information, and then you update the weights and then go through another loop. So, you know, hopefully this process makes it easier. And then we go to not a comparison. Then we go to sigmoid function. So what sigmoid does is, say, instead of the activated value, instead of letting it to go far off, because if the value is at a very high scale, 1,000, it's not going to help too much. You know, at that level, the difference is going to keep increasing if you have an extreme value for Z. So it doesn't help. So why don't we soften the tail? Why don't we make it like that? Right. And when Z is 1,000, it doesn't matter what the activated value is. The larger the worse. So if we kind of cap it here, then it won't keep increasing. And then the feedback is that if the true value is 0, or let's say so if the true value is 1 and Z is very large, then the error is negative. It needs to break down. But if you use a new function, it's going to be very close to the error is very small. All right. I will have to resolve this point to myself, but the point here, the point for the sigmoid function is that the errors, the computation of the errors does not have to be too large. If the activation can map the Z net input onto a fairly small region, then the cost function will not explode. So the learning process can be more stable and easier to manage. So that's the only that's the main advantage of that. But the disadvantage is that the gradient calculation process becomes more tricky, because you have the exponential and you have the division there. So it's nonlinear transformation, nonlinear activation, and to derive this function becomes more tricky. So the gradient becomes more complex. But it's still a closed formation. It's a closed formula. It's just more complex. That's all. But the advantage is that now you can avoid extreme values of cost function. The learning process becomes more stable and smooth. All right, so coming back to the for loop. Question 7 asks you to do the for loop for multiple epochs. So you will need to put the codes together, but luckily you have these complete codes in the demo. I'm going to copy it here, and then just to not mess around with the costs, to not mess around with the questions, replace the comment. And this should be fine, I think. If it's initialized properly, you can run this without issues. And then what's new here is there is an empty list to store the cost values in each iteration. We have 15 iterations here. So the cost value can be, you can save 15 versions of the cost value and you can plot them. All right, let's run it. Takes a second. And then the current weights are that. And then this will graph the cost curve. So it's nice. It's big drop at first and then slower movements, but smooth, slower movements in the end. All right, and if you want to confirm the cost for now is 116. Are we good? Are we good? Okay, so let's see. So the next question adds the L2 regularization. So what you need to do is to first of all understand the L2 process and also why overfitting occurs. So let's talk about overfitting a little bit here. The demo codes using the default data set tries to demonstrate the possibility of overfitting. So what happens is, if let's say the algorithm, the legit regression algorithm is still powerful, it's strong, the data set is simple, data set is not complex. So let's say if I keep running, beyond the 10 epochs, at the beginning, it's the kind of become worse and then quickly learn and get on track. If I keep learning for a long time, the cost will keep dropping, although with a slower rate, right? But if I just keep learning and learning, would that be possible that the algorithm makes zero mistake? As long as there is some cost, the algorithm is making some mistakes, right? When the cost is zero, then, or the cost is close to zero, then the mistakes are minimized. So the experiment is to run the algorithm for 10,000 times, or the epochs is 10,000. Run the same algorithm, and then the cost is close to zero. And when you take a look at the train set accuracy, which is the percentage of correct classifications on a training set, you get 100%, which means the algorithm is able to figure out which variables are critical and the optimal weights that you should assign to those variables to be able to guess 100% correct. Now, does that mean overfitting? What do you think? So think about it. If the model after training for a long time, it is able to 100% correctly predict the value or guess the target label. Is it overfitting or is it not? You know, is a model able to perfectly predict the outcomes? Question. Depending on the problem, yes. Depending on the problem. Later we'll talk a few more concepts to kind of unpack the concepts. But the truth is, for this problem, it's not overfitting. This problem is simple in the fact that the cases, you know, you can read them here, but to put it simply, if you map the points of this data set and find the correct variable, only 2 or 3 variables make a difference. If you find those variables, then you are able to draw a simple line to separate the 2 cases, true and false, churn, this case is default and non-default. You are able to separate them clearly in the training set and even very closely, perfectly on the test set. So this problem is made simple to the sense that given enough learning, the algorithm is able to figure out which variables are important. Those variables that are important will have a bigger coefficient. I think that's somewhere, print out the coefficients, but not here. But anyway, so both the churn and the default data sets, there's a way for the algorithm to learn perfectly. That's great. And when you apply the model on test set, the performance is also very good. So in that sense, the bias is low. The bias is the difference in performance of the same model between the train set and the test set. The bias, the difference in performance didn't drop too much for the test set, which means overfitting is not happening. So that's only for this case. In any of the real data mining real projects, you would never, even for the projects, even for the course projects, you would never expect to get 100%. If you get 100%, you assume there's something wrong. You assume there's something wrong and you try to find the cause. You know, more than often, one of the reasons that you get 100% accurate on the training set is because, you know, you mistakenly included the target variable in the X variable. The target variable is the only information you need to correctly predict the target, right? So if you mix the target variable into the input variable, the algorithm will learn it and it will make perfect predictions. And that's not right, you know. So as soon as you find 100% accuracy, there's a problem. You need to fix it. Not the problem here, but elsewhere. All right, coming back to, so L2 regularization is a mechanism to reduce overfitting. It's not to detect overfitting, but to reduce overfitting. But what is overfitting? Again, so overfitting in the context of logistic regression model is where the model somehow figure out that by emphasizing some of the variables under some conditions, you can perfectly predict everything in this data set. Now, this is not likely to hold in other data sets, even on the test set, because there are random chances that make it perfect in this data set, and somehow the algorithm found it. You can only find it by training a long time. Then the algorithm has, opportunity to discover that, but that would not hold. So what happens when you have an overfitting model is you have a few coefficients that are very large that emphasizes those particular variables for this data set. You apply the same model to the test set, the model will fail miserably. And that's when overfitting happens. So one mechanism, which in fact is the regularization, the logic is if we constrain the algorithm in a way that the coefficients will not become too large. So kind of put a cap on how much the algorithm can allow the coefficients to grow, then you somehow will fix, at least you'll prevent overfitting to be too much. So the mechanism here is to build the size of the coefficients into the cost function so that because you are trying to minimize the cost function, at the same time, if you increase the size of the coefficients, you can minimize part of the cost function, but you will increase the other parts of the cost function, which is against your purpose of learning. So through that learning process, by reconstructing the cost function, you achieve at some level to avoid overfitting. To see the point, let's take a look at the slides here. So if you flip the slides into regularization, there are two common forms of regularization where you add a term to the cost function. Now, the cost function is sum of squared, and it's supposed to be minimized. If you add these terms to the cost function, it's going to constrain how much the cost function will be minimized. These are sum of squared of the coefficients. So you simply add squared coefficients to the cost function to act as constraint for the cost function to be minimized too much. So that's the basic logic. And because of this, your let's say logistic regression notes, your two formula will change. One is the gradient with the, no, this is not regularization. So with regularization, your gradient for the logistic regression will not only have the regular gradient formula, but also an additional term that's the derivative of the L2 regularization. That's one thing that will be changed. The other thing that will be changed is when you calculate the cost function, it will have the additional squared coefficients. So reflecting on the codes, if you look at the regularization somewhere here. Do I have it? Let's see. Maybe not here. Let's see, L2. Okay, here. Implementing logistic regression with regularization. You will have an additional parameter here, L2 prime. So with that, you have two different formula. The gradient has an additional term. The cost function, here I'm using an end of line. The cost function also has an additional term in the end. So make sure you have that. Once you do that, you can, check the results. And all right, last point. So calculating the accuracy for both the train and test sets, I think I need to run this anyways. So let's do that. With the with these should be fine. Okay, and then make sure that your bias after 500 epochs is close to minus 6.95. All right. So with the updated weights, now we can calculate the model performance. Here it's the accuracy. So what happens is for the train set, you go through the forward prop, which includes the net input, activation, and make predictions, which uses a threshold function after the activation. And then after you calculate the accuracy, you don't have to do these. After you have the accuracy, you can simply print the accuracy out. So that is the train. And make sure the data objects are the same. Y train, Y pret. And then for the test sets, you do the same. And pay attention to the fact that all these data objects, Z and Z clip and Z act, Y pret, accuracy, they are reused after calculating for the train set. They are reused in the test set. All right, but they should not be a problem because you don't have to store them. You only have to calculate and print them. And here, it's an opportunity that you can improve the process here. So the activation process is different here, right, from the aniline. And then because of the two steps that are involved, it will be easier if we define a sigmoid function. So we have a sigmoid function somewhere here. Let's see. Sigmoid function, so you can copy over here and define the sigmoid. And then you can replace these two lines with one simple line using the sigmoid function. So using z to call on sigmoid as defined here, which is exactly the same two steps, and then returns the zx. So you can do the same here for the test sets. And then let's run. The accuracy on the training set after 500 epochs is 96.6%. On the test set is 96%. So these would be the correct solution that you want. So on the churn set after 500 epochs, the model is able to figure out almost optimal weights to lift the accuracy almost to 100%. And the difference between the training set and the test set, the difference is not too much. It's only 0.006 or 0.6% difference. So the model performs equally well on the train and test sets. It's almost making perfect predictions on both sets. There is no overfitting here, but this is the special case because the data set is simple. In real data sets, this is not going to happen. Okay. So that is all. Through the homework 2, hopefully the process is illustrated clearly, and the coding adaptation process is critical here, as you can see. Whenever you have inconsistent results, pay attention to several things. Have you changed the data set name? Have you forgot the negative signs? Have you forgot the parentheses sometimes? Have you updated the column names? Things like that. So those are what you will most likely find the bugs. All right, that is all. Let's all right, I'll be here if you have questions. Otherwise, enjoy the rest.